Good afternoon. This is CIVE 634, and this is surface water hydrology. And the class, this is class number 062. And the subject today is hydroclimatology and drought. So today we are going to continue on the subject of hydroclimatology. And I had already covered the paper, Is Vegetation Paying Its Own Way? By the way, I consider this paper to be very important. And if it's very important, it probably will be on the exam. That's number E05. But today I'm going to start with E07. I will skip E06 because that's the video, and I already covered that ground. E07, 8, 9, and hopefully 10, 11, and 12. I'm hoping to get all the way to
Ponce.
Column. Okay, fine. I got you.
Thank you.
Got you. Column, you missed the details of the exam, so please check with your classmates after class.
Will do. Thank you.
I already explained the details of the exam. However, this Monday I'm going to repeat that again, so you're not going to miss it. Okay, so let's go back in here. So the first one, the first item that we're going to cover today is a video and a tale, but I'm going to look at the video here because it's short, sweet and short. I'm going to be, this subject is advective precipitation. This is a kind of an interesting story, which I think you would appreciate. Okay, so let's go for it. Advective precipitation. This is a concept that originated with Boudico. Prior to Boudico, it was just precipitation. Now, Boudico's concept dates back, realistically speaking, it dates back to 1953. But it was not until 1995 that it was brought into, I guess you could say, the mainstream of hydrologic science in the world. It was endorsed by the people at MIT. I studied it in the middle 90s, and I had already been looking at it for about 5 years. So that's lend source to the story that we're going to tell in this video.
In December of 1993, I was invited to lecture at the National Institute of Hydrology in Roorkee, India. My presentation was titled, Management of Floods and Droughts in Semi-Arid Regions.
Interestingly, I had just come to India from Brazil. I had spent 2 months in Brazil studying droughts. And the reason for that, and we're going to cover this more extensively later on within this group of classes in hydroclimatology and drought. But I was in Brazil to study droughts because I found out that there's a very good and world-renowned agency that studies droughts out there. And I figured I was going to get a sabbatical, so why not just go to Brazil to where people really know what they're talking about in droughts. They have a lot of experience, have a lot of work that they had done over the last, I'd say, 80 to 100 years. So I was in Brazil, and then right after Brazil, I went to India, and because I was kind of in the middle of my sabbatical, it was at the end of December, I think. And December, we were free. So I was asked to give a lecture out there, so I gave a lecture on droughts because it was fresh. The subject of droughts was fresh on my mind had I just come from Brazil.
2 years later, in 1995, I followed with a related paper entitled Management of Droughts and Floods in the Semi-Arid Brazilian Northeast, the Case for Conservation. The theoretical concepts were presented in the paper Surface Albedo and Water Resources, Hydroclimatological Impact of Human Activities.
This is the paper we have already reviewed, I believe, Monday.
Published in 1997. key element of the theory is Budico's model, which separates precipitation into its advective and evaporative components.
Here, precipitation advected, and precipitation it comes from evaporation and recycled precipitation. So there's two components of precipitation. This is, of course, originated in Budico's hydroclimatological model, which we have already discussed. And the A of advective comes from advected from the ocean. Because from the ocean it is advected. Now, advection is an interesting word. It is a word that is much used in fluid mechanics. It is also expressed as convection. So if you have heard convection, it means kind of the same as advection. So what's the difference? I don't really know the difference. All I can tell you is that in fluid mechanics, in hydraulics, we usually refer to it as convection. But when the mechanics of fluids is of compressible fluids like air, people in that field call it advection. So that's the only difference. There's no difference in meaning. It's just usage between advection and convection.
A crucial step is the quantification of the water vapor advected into the control volume. At the end of the lecture, one of the participants confided to me, "Professor Ponce, I have been in the field of hydrology for about 10 years and have not heard anybody talk about advective precipitation."
Obviously, if you're not talking about Budico's model as a way of modeling the hydrologic cycle, you're not talking about advective precipitation, right? So I thought that was an interesting story. So that's the first subject that we have here tonight. And then the second one is also interesting and really kind of fascinating. And this one's called the Untimely Drought. We also have it in vector as well as in raster. I'm going to go with the raster this time. The untimely drought. Drought is always going to come back. That we know. What we don't know is its intensity, duration, and frequency. I do believe that IDF functions of drought had not been done until I wrote that paper in the year 2000. That I believe. IDF for precipitation, very extensive treatment in many books, including my own book. Maybe 100 years of IDF in precipitation, but not IDF, precipitation and related to floods, but not droughts, for some reason. So we undertook to do this study of IDF for droughts in the year 2000. Let's take a look and hear what we say. Don't forget the IDF refers to intensity, duration, frequency. So how often do the droughts come in this particular region? Or how long do they last, right? Or how severe they are. Are they light or severe? And if a drought continues on for more than 3 or 4 years, it becomes very severe. The severity is measured with a certain parameter. And by the way, drought has a way of being largely unpredictable, meaning we have some idea as to the frequency and so forth, particularly the frequency. And the duration, some other idea. The severity is more difficult for us to assess. And yet, we cannot completely rely on all the studies that we have made. We have to wait for the drought and find out how is it going to be.
Navigation on the upper Paraguay River between Cáceres and Mato Grosso.
I think we missed it. Let me go back.
Cáceres and
Okay, here we go.
Navigation on the upper Paraguay River between Cáceres in Mato Grosso and Porto Murtinho in Mato Grosso do Sul, Brazil, has been a concern of many. In the late 1960s, the United Nations Development Program, UNDP, funded a 5-year study to collect hydrologic data on the Upper Paraguay.
UNDP was interested in funding navigation projects in the Upper Paraguay. This is the Upper Paraguay. That means it's upstream of the Paraguay River, okay? And the Paraguay River is upstream of the Paraná River, which exits and goes into the ocean, into the Atlantic Ocean in Buenos Aires, Argentina. Okay, so this is Ladario in Mato Grosso do Sul, Brazil, the town or city, I guess you could say, of Ladario, and that is the Upper Paraguay.
With the intent to use this data in future navigation development projects.
Exactly. I guess somebody figured out that you can't fund the navigation projects unless you have data, good data. And there was no good data. So the first thing that the UNDP, the United Nations Development Program, did in the early 60s was fund a 5-year study to do hydrologic data, to collect hydrologic data, both water and sediment.
The project was initiated in 1968, ending in 1973.
They funded 5 years of study.
With an expenditure of about $5 million.
$5 million at the time. Now it'll be 15 or 20 at this time. That's 50 years later.
Yet the Upper Paraguay was not to be tamed. The river.
This is a record of Ladario, and I was going to say it is a complete record, but it's not really complete because it goes to 2013. Can you see that? 2010, 2013. And I do believe we now have a graph that goes all the way to 222. I just got some new data. Every couple of years I get the data from people in Brazil that I know, and I augment or add to this chart that I put together in the year 1995. So this chart ended in 1995. It ended over here, and over the last 1995, over the last 27 years, we've added these points in here to the graph. Okay, so this is the complete record at Ladario.
Remain in drought from 1962 to 1973.
So what we're saying in here is that the river, it decided to do a drought, and the period of drought covered exactly the period of funding. So the entire period of record, 68 to 73, was done for a dry period, for the driest period of the river. Can you see the driest period over here? So of course they could not tell. They didn't know. They just said we're going to do some measurements on the river, and they could have known that they were in drought, but they didn't know when the drought was going to stop. Perhaps in their wisdom, as I always say, they were hoping that perhaps the drought was going to end and they would be able to measure sediment and water and sediment parameters throughout a wide range in stages. But that didn't happen because the drought remained exactly from 68 to 73 is over here, and it was still drought. This is 73 over here. It appears that after 73, the river decided to go exit the drought and go over here to the top.
The longest of record.
Now, if you, interestingly, because we've studied this extensively, if you look at this chart, there was a drought here in 1910, 1915, a little bit. Then there was one in 1940, 42, 44. I remember people telling me, because I interviewed a lot of people in the field, they told me this Farolete Balduino, that is a famous site out there next to this site, next to Ladario, had uncovered a bunch of rocks in the year 1944, which is over here, right here. So the rocks were under the surface, And by the time, at this point, the gauge was -0, it was negative. This is the zero gauge, and it was negative already. Negative in the gauge means drought. Okay, so it got over here, and rocks were uncovered, and we've done extensive study on the control, on the geologic control of the upper Paraguay. We did 2 or 3 studies on this over the last 20, 30 years. So they missed it, but they missed it just because. I mean, droughts cannot be totally predicted. We know more or less how it happens and so forth, but it cannot be totally predicted. For those of you that are not familiar with this chart, I'm going to tell you how it works. The white dots are the lowest point on record, and the black dots are the highest points on record. How come this record is not, it looks like it's going from high to low and low to high, right? That's because the stage, the variation of the stage at this point, which is kind of in the middle toward the southern part of the Pantanal, downstream, it's a total and complete sinusoid. So it goes up once and it comes down once. The period when it goes up is typically in June. And when it goes down, typically in November or December. But the date of maximum and minimum peak, or rather, maximum stage and minimum stage, could vary 1 to 2 or 3 months, depending on the hydrology, depending on the stages and so forth. Actually, it depends on the friction, but the friction is determined by how high the stage is. Because in this system, it overflows readily. So when it overflows, it goes into the valley. And if it goes into the valley, the friction is going to increase. And therefore, the flow is going to slow down. So that we know, and that has been documented throughout the Paraguay, particularly here at Ladario. Now, I'm also going to say something interesting in here, that if you notice over here, I'm going to grab this because otherwise, if I don't grab it, it returns. If you notice, we are missing a drought since the early 70s. Here, there's no drought. We predicted, again in our wisdom, we predicted that if this pattern was going to repeat itself, that the year 2000 was going to be a year of drought. That's what we said. And we said it, I believe, in papers and reports. But it didn't happen. Professor Ponce missed. And I have no problem missing the occurrence of a drought. I know I've done this many times, and I missed probably half of the time. Okay, so we missed it. We didn't know what had happened here. We couldn't tell what nature was doing. I surmised at the point that it was raining too hard or too much because of global warming, the culprit, or there was a lot of development, and development had brought in a lot of sediment because development also always causes sediment movement. You break the natural vegetation, you produce agriculture, and agriculture always produces more sediment. That is without saying. Okay, so that development would have caused sediment to come into the bottom of the river, at which time it would have raised the same amount of water had to come through, so it would have raised the stage. We don't know at this point whether the sediment was the cause or whether it was global warming the cause. I thought that the Brazilians should do a study on this to find out exactly what was the reason for the drought now wanting to come back, because it's 50 years, 1970, 2020, 2010, it's not there yet, okay? But to my knowledge, this study has not been done or has not been shown to me, okay? But the story has a good ending because we have been plotting very carefully these numbers. And these numbers showing here all the way to 2013, but I actually have the latest graph to 2022. And you know what? The last year and a half have come below zero. Meaning, if I had to show you these, it would go like this, it would up and down, and by the time you get to 222 over here to the right of 220, the gauge, the lower gauge, the minimum gauge is below zero, 2 times. Which leads me to believe that it was about time for the Paraguay to go into drought stage. And I do believe that is the case. Of course, don't take my word for it, because the river could go back and bounce back and go high. But I don't think so. I don't think so. It's just going to do what it has done in the past. And luckily, we have this data going back all the way to 1900. So that's good data. And it's a very nice and complete data. This data is put together the Navy, the Brazilian Navy, they have a station out there in Laudario because the Paraguay is the upper Paraguay happens to be the border. 80% of its course is the border between Brazil and Bolivia on the left side. So that's the end of the untimely drought.
The untimely drought on the upper Paraguay meant that the 5-year study was only able to collect data during low flows. Thus, the moral of the story. Quote, when dealing with the weather, be prepared to lose. Unquote.
That I showed you there was the Laudario light post. Okay. So the next paper that we're going to review in here, it's an article that I wrote in the year 2007, question and answers on the return period to be used for design. Now we also have this in raster form, but I'm going to use the vector because it's better from an educational standpoint. I think it's going to be better because I can stop and you can see the words and so forth. I think it's going to be better. But I encourage you as a compliment to later on your own time to watch the video. The video basically says the same thing. It's a long video. It's about 15 to 20 minutes. Okay, so we're going to pose questions and answer them on the return period to be used for design. Why did we do this? We had a project in the year 2007 in all places in Baja California. And then the question arose at the time, and what was going to be the return period for the project? So I looked around and realizing that everybody knew the return period, but there was nobody out there that had done what I was doing in here, or what I had planned to do, question and answers on the return period. So I sat down, and maybe a month or two, I put this thing together with documents and so forth. It is designed for people that want to run with the knowledge, not necessarily ask too many questions, people on the go, consulting firms, people that are consultants in hydrology. Several people have told me afterwards that this is a very important and very good, useful piece of work, by the way. And I think you'll find that it is also. I guess you'll agree with that assessment. Okay, first question. What are the return periods commonly used in design? Everybody talks about return periods, but it is hard to pin down exactly what return period you're going to use. And you have to. Anytime you design a project, you're a hydraulic engineer, or even geotech engineer, you're going to design an earth dam, you need to figure out the hydrology in order to design the overflow spillway and so forth. Let's not forget that engineering projects occupy different types of civil engineers. The straight civil engineer, the hydraulic engineer, the geotech engineer, the planning, the agricultural engineer, or the agronomy and so forth. There's all kinds of professions, technical professions, that go into the design of a large project. So be it. Okay, so in hydrology, design return periods vary typically from 10 to 100 years. And in countries or places where the probable maximum precipitation has not been defined, up to 10,000 years. Why do we say that? Because in the United States, we don't use more than 100 years. If it's already 200, if we want anything higher than 100 years, we would go with fractions of the probable maximum precipitation. To tell the story, up to the year 1960, we were using frequency-based determination of floods, or flood determinations. But in the 60s, NOAA, the National Weather Service, decided that they did not trust the data because the data was only 80 to 100 years long. And nature has been around for more than 80 to 100 years. Okay, a lot longer. So they figured, 1% of the data that we need is not going to do it. We don't have 10,000 years of data, right? The most that we had here in the Western United States at that time was 80. When we did the Santa Cruz Basin in 1985, we only had 80 years of data. We went ahead and did it anyway because there's nothing else that we could do. Okay, so we have, in the United States, we have a probable maximum precipitation. But in other countries, they have not gotten around to putting it together. It takes a lot of expertise, resources, and so forth, knowledge and resources, to put the whole theory of probable maximum precipitation. The National Weather Service started in 1963 with their first work, which was called Probable Maximum Precipitation in California. I believe that prior to California, they did, I believe, the Virgin Islands and Puerto Rico. I don't know why. Don't ask me because I wasn't there at the time. But California is considered to be one of the preeminent older versions of the PMP, 1963. After they did that, they did every other state. It took them 20 years to do it, but they figured, and they finished. They produced these hydrometeorological reports, number 1, number 2, there's about 50 of them that are in the literature. As a matter of fact, I have a list on my website of all the HMR reports, because at any one time, we have actually collected and studied those reports. As a matter of fact, I had to study them. No, I take that back. I studied the California report because I put it in my book, in chapter 14 of my new book, my online hydrology book. I decided to do, as an example, the calculation of the PMP for California. Interestingly, NWS, the National Weather Service, that I already told you in 1963 did their first issue, they found that it was necessary to review the first issue, and in 1998, that is 35 years later, they came up with a second version, which superseded the first version. So 1963 version is no good, no longer anymore. Why is that? Well, I think the reason was because since California, the PMP for California was one of the first ones that they did not really do a thorough job, because, at the beginning you're kind of learning. And then after that, they did so many studies on so many states that they figured that I think they decided that they had to go back and review and revisit the California PMP, which they did in 1998. My book online already has an example of the California PMP calculation. Very complex calculation, by the way. Okay, so the choice of return period depends on the size of the drainage area. That has to do with the importance of the project too. The risk of failure. In some places, we want to lower the risk of failure. In some others, we want to increase it. That depends. So the risk of failure is something that the designer chooses in accordance with the owner. Be it the state or being a private owner, the owner always has to say as to how much the project is going to cost. Typically, owners don't tell engineers, go give me a project and you figure out how much it costs. No, the owners tell the engineer, go get a project, design a project, and make sure you bracket the cost between these two numbers that I already worked out. That's the money I got. So you got to work within what we have. That's the way it works. That's engineering. It's not science, it's engineering. The importance of the structure, yes, and the degree of conservatism in the design. Some people are more conservative than others in everything, in the design and so forth. So those are the 4 factors that affect the choice of return period. What is the lowest return period? The lowest return period applicable in urban drainage is 5 to 10 years. Why do we say that? Because when the return period was being considered initially for design purposes, that was in the year 1955, I believe. And ASCE came up with a manual. The drainage manual of ASCE, dated 1955, starts with 5 to 10 years return period. And that has kind of been cemented into the literature. 5 to 10 years is the lowest you could possibly choose for design purposes. It is low. But we'll explain later on why. Why don't we go 100? We'll explain why. Typically, these return periods are associated with drainage areas smaller than 100 hectares, which is 247 acres, which is half a square mile, roughly. 640 acres to a square mile, so 320 in U.S. customary units. 247 would be 100 hectares. Since we are talking also in terms of SI units, we rounded up 100 hectares is 247 acres, roughly, okay? Nobody's gonna ask questions about minor details. For these areas, for small areas, the rational method may be used to develop a peak discharge for design purposes. And it's done all the time, all over the world, since 1889, when Kuchling, I believe working out of Ireland, I hope I'm not incorrect in here, Ireland, right, developed the rational method, which was a conceptual method, basically. The rational method is a conceptual method, it's not empirical. And that's why it was called rational, because the methods that were available prior to the rational method, in my mind, were irrational. They were empirical, meaning anything could happen. You can pick up a number. It was a guess. It really was kind of a guess. It was based on empirical data. And anything you based on empirical data is odd coefficients and exponents, and you can only apply to the location where the data was developed, for which the data was found. Number 3, very important and difficult subject. You know, when I say difficult, it is difficult. So I want you to read this number 3 later on. Read it 2-3 times, hoping to understand perhaps what I had said. And I tried my best to be as clear as I could. I always try, but sometimes I can't make it because it's tough, okay? In small watershed hydrology, the peak discharge is related to the time of concentration. And through the applicable intensity duration frequency, IDF curve, to the rainfall intensity, because the intensity is related to, comes from the duration, which is coming from the time of concentration, so we're kind of all related. Small drainage areas have a short time of concentration, that is for sure. And this produces a high intensity, right? Through the IDF curve, since the IDF curve is hyperbolic, it produces a high intensity. Since it produces a high intensity, it consequently has a high peak discharge per unit area. However, since the area is small, the peak discharge will be correspondingly small, because you can have a high intensity per unit area, but the area is small. The smaller the drainage area, the less likely that it will be visited by a high intensity precipitation event. That's the crux of the matter here. If the drainage area is small, it will not be hit by this huge rainfall, because it's too small to be hit, right? Rainfall doesn't selectively choose to go here. If it does, it goes, but it doesn't go there all the time. It has other places to go. Thus, for small areas, with the time of concentration measured in minutes, it is usually not economical to design for long return periods. So it's really a question of economy. That's why we don't design, that's why we use 5 to 10 years from the beginning. Maybe 25, but still 25 is kind of low compared to 100, is certainly low. So then the issue is, why do we continue to use 5 and 10? And the answer is because of economy. We're looking at a culvert. We want to design a culvert. What will be the frequency? 5 to 10 years. For regular, nice culvert, 5 to 10 years. Why? Because this means that in 10 years, every 10 years, roughly, on the average, the discharge will be exceeded and somebody will get flooded. But we assume that that is not as much compared to the size of the culvert. We could make the culvert twice as big, but that then will be at 25 years and it will fail every 25 years. But long story made short, we design culverts in particularly with small frequencies, rather low return periods or short return periods. Number 4, what is the return period for regional flood protection works? Now, regional flood protection works encompass large areas. So in that case, we have to go higher than 5, 10, and 25. Typically, we would go to 50 or 100. Example, here we have levees on the Tecate Creek, Baja California. You know, Tecate Creek is an interesting binational river. It originates as Campo Creek in the United States. Campo, East County, East San Diego County. You have been, presumably, to the city or town of Campo out there in southeast San Diego County. It's a little bit west of Boulevard, and you may have heard of Boulevard out there. I've done a lot of work in Tierra del Sol for almost 10 years, so I'm very familiar with the area. So I also did the drainage or the hydrology back in the year 2001, I believe, of the entire Campo Creek, all the way from, because Campo Creek eventually goes through Campo, I'm sorry, goes through Tecate, first to Campo, then through Tecate, crosses the border, goes to Tecate, and then it comes back, and it goes to the United States. It returns back to the United States, at which time it joins with the Cottonwood Creek, which comes from the north in the U.S., and they form the Tijuana River. The Tijuana River. And interestingly, and this has happened before, the Tijuana River forms in the U.S., but then when it goes back into Mexico, because the river S's throughout the border, when it goes back into Mexico, it loses its name and again becomes the Tijuana River. Actually, Alamar. It becomes the Alamar River. I was forgetting the name. It's been 20 years since I studied this. It becomes the Alamar, and then when the Alamar goes into the United States, then it becomes, again, Tijuana. So the Tijuana River has two births, one in the confluence with the Cottonwood and another one in the confluence with the Alamar. And by the way, the same thing happens with the Amazon River. Long story, made short here. So the levees on Tecate Creek, Baja California. Levees. What is a levee, in case you guys have not considered that word from a technical standpoint? A levee is a wall, typically earthen wall, constructed with loose materials. But they are stable in the sense that they're designed by geotech engineers to be stable. So here we have a good example, because it's a nice kind of sweet example of a levee, which is on Tecate Creek in Baja California, downstream of Tecate. So the city of Tecate is right here somewhere. So this is the Tecate Creek on its way back to the United States here, looked from downstream. This photo was taken in the year 1903 when we were doing studies over. So as you can see, that's a river. That's the levee. What's the purpose of the levee? The purpose of the levee is not to allow the river to overflow. So will the river overflow? Yes, the river will overflow when it supersedes the levee. At which point, I hope that these people behind know how to run, because they got to run. Because had there been no levee here, it would have flooded, and they don't need to run because it's a slow process. But if the river charges the levee and it overflows the levee and it breaches the levee, those people in the back of the levee, on the other side of the levee, are in danger of dying, of drowning. And that is the case here in Tecate, in the United States, in the Mississippi, all over the world. We have a lot of experience with this, with levee design and levee engineering, levee hydrology. And I believe I did show some, I'm not sure if it was this class or the other class. Now I'm getting really confused. But I did show the breach of the levee in Ohio. No, it's not Ohio. It's Illinois in the year 2011 when I visited and I produced that video that I may have shown you. If not, I'm going to put it for you to see on the video list. Okay, let's move on in here. What is the return period for highway design? For highway design, the return period depends on the importance of the structure. Return periods in highway and other regional transportation infrastructure typically vary from 25 to 100 years. It is unusual for highway drainage to use periods longer than 100 years. So 100 years is considered to a ceiling where we get there, because if we wanted to put some security or assurance into the project, highway project. If a highway floods, there's a little problem, but not a whole lot. We're always considering the issue of how much is it going to cost. And that's included in the project, because as I already told you earlier, the cost of the project is typically determined before the project is ever done. The owner, the state, be it the state or a private person, always saying, I got so much money. This is all we can spend. So you try to stay within those bounds. Number 6, what is the return period for bridge design? Now, in the case of bridges, it's a little more complex, because like in this bridge over here, if the bridge were ever to fail, you will have dead people over there. You see those buses over there going over the bridge? And that it's dangerous. And it has happened, by the way. We have had situations all over the world. Here in the United States as well, we had one in Italy 3 or 4 years ago where a lot of people were killed. That was not an issue with the river, but it was still a bridge failure. So bridges should be carefully designed and put together. In the case of river spanning bridges, because you know have a bridge that spans a river and one that does not, the focus shifts from the size of the drainage area to the importance of the structure and the risk of failure. For the design of bridge piers, return periods up to 500 years may be justified, depending on the individual case. So 500 years, I've seen this happening, 500 years. Why? Because there's a whole lot of things that we don't know in regards to sediment flow. Remember, I already told you there's a large range of variability in the calculation. So we want to be a little bit safer than we normally would in any other case. So we jack the number up to 500 years. And if anybody wanted to do a design for 1,000 years previous consultation with the owner, who may be the state or a private individual, typically the state, then they can do it. Let me give you an example. The country of Mexico decided to improve the highway that goes from Mexico City to Acapulco. They did that 10 years or maybe 8 years ago. And within 2 years, they had a huge flood in one of the tributaries. I mean, the road was about like 300 miles long, so we probably had a bunch of bridges. Well, one of the bridges failed miserably after 2 years of having been built in the new road that linked Mexico City with Acapulco. My guess would have been that it was prior to the pandemic, maybe 2 years prior to the pandemic, but you can check it on the web. Just go ahead and Google failure of the bridge near Acapulco, circa 2017, and they'll show it to you with all detail. Okay. What is the return period of 100 years? The basic number that everybody throws around, the 100-year flood, the 100-year flood. So when did this concept originate? Who was the culprit? Let's talk about it in those terms, because I like that word, because I'm going to come back and you'll see it used by them, not by Professor Ponce. The return period of 100 years amounts to 4 human generations. The generation is considered to be 25 years. It is a number which is not too high nor too low. 4 human generations, oh, okay, fine. The value of 100 years does not mean that the structure will be at risk exactly every 100 years. Rather, it means that the structure will be at risk, say, 10 times every 1,000 years. So it's not gonna, by clock, fail every 100 years. No, that's not the way it's gonna happen. But if you take 1,000 years, the 100-year flood is likely to recur 10 times in the mean. The 100-year flood applies for floodplain development, medium-sized flood protection, and regional urban drainage facilities. So it's a big number, more so than 50 or 25, but then one that is very commonly used in practice. Where? In the United States and by and large throughout the world. As a rule, the larger the drainage area, the longer the return period. Typically, drainage areas less than 250 hectares do not warrant return periods greater than 25 years. We already talked about that. We said that. However, larger areas up to 10,000 hectares and beyond, and you know, you can have a huge watershed, much more than 10,000 hectares, which is only 100 square miles. Beyond may justify return periods up to 100 years or longer. So 100 years is a number that has been used as a reference. Less than 100 years, more than 100 years, a good reference. How did the concept of 100-year return period originate? Let's go back to history. The idea of setting a return period of 100 years as a norm for flood calculations in the United States is widely, but presumably not entirely accurately, attributed to Professor Gilbert F. White. I managed to get a picture of Professor White from the web. He was a professor of geography at the University of Colorado, I believe. He was a good guy and a very well-known guy before he passed. In the year 2005, he was interviewed by Martin and Rose, I think it is, in a book. And the book was called Interview with Gilbert White, which, by the way, if you're interested, I don't think you would be interested, by page 57. Page 57 has this quote in here, which I'm going to read with you. The interviewer was asking, Martin Rose was asking all kinds of questions because he wanted to put the book together. And this was basically the book that talked about the interview. So this is the answer that Gilbert White gave at the time. The question was, how did this idea of the 100-year flood originate? Where did you guys pick it up or pull that out? So this is what he said in the book. There was a very interesting development of the notion that there could be a flood of sufficiently low frequency that no effort should be made to cope with it. And how interesting. In other words, at the time they were talking about 25-year floods, which is within the lifespan of an engineer. And they said, well, it's not enough because we continue to have floods. So let's jack that up to 50, maybe to what? What can we jack it up more than 50? Okay, and then the idea came up of 100. And they said, like he says in here, he repeats that, he says, we shouldn't make any effort to cope with it because it's too much. So we're going to live with it, with a 100-year flood. Now they don't do that, though. Now they're trying to protect the society against the 100-year flood. But at the time, as you can see, the origin of the concept was, it's so big that we're not going to worry about it. The Federal Insurance Administration, because at the time there was a lot of action in flood insurance, 1950s, 1960s, picked 1% of a recurrence interval, that is 100 years. And some of us were involved in that, and some of us were involved in that because we recognized they initially had to have some figure to use. Basically, this is the way it happened. The Federal Insurance hired Gilbert White to tell them what to do. Why? Because he was a well-known guy in the field, you know, flood, geography, frequency of floods, and so forth. So he came up with 100. But he's telling us the story that he didn't do it alone. He said, one of us, we recognized that we had some figure to use. The 1% was chosen. I think, and this is him talking, I think Jim Goddard and TVA colleagues, TVA stands for Tennessee Valley Authority, one of the 5 or 6 water agencies in the United States. The only difference is that TVA only applies to TVA, the Tennessee Valley. So they don't have a lot of, well, in the past they were more, I guess you could say they were paid more attention because they were building the huge dams. But there are no dams to be built anymore. So I would say TVA was very important in the 20s, 30s, 40s, 50s. By the 70s, their importance had already subsided. I think Jim Goddard and TVA colleagues would be considered parties to the crime. With the lack of any other figure, the concept of TVA's intermediate regional flood, meaning the intermediate value, be more than 50 and less than 200, seemed a moderately reasonable figure. We generally use the term catastrophic flood for events of much lesser frequency, meaning the PMP, which leads to the PMF. PMF stands for probable maximum flood. So what is the PMP? Probable maximum precipitation. Stands for probable maximum precipitation. Even though its name implies a probability, in effect, the first P in PMP is to be interpreted as possible. What is this? Is it possible maximum flood or is it probable maximum flood? Well, the story that I have read is that originally they were going to call it possible maximum flood, but they switched it and they call it probable maximum flood because they didn't want to be sued afterwards by somebody coming in. Wait a second, you said that this was the maximum possible and we now had an event that is higher than what you said was the maximum possible. So they didn't want to get into liability. The National Weather Service didn't want to get into liability, and they said, we're going to degrade a little bit this concept, and instead of calling it possible maximum flood, which is very, how can I say, there's a lot of chutzpah to call it possible when you don't know what's going on, right? So they call it probable maximum precipitation. That's the origin of the term. And it has withheld the passage of time. We continue to use it, and it's a very good concept, actually. Unfortunately, it's not used all over the world because those people out there in many countries of the world, don't forget there's 240 countries out there. They don't have the wherewithal to do the study, the study for the development of the PHP. I do not believe even Mexico, that is a large country, our neighbors, they don't have the PMP. They still use P10,000. The PMP is a reasonable maximization of the event precipitation expected at a given geographical location for a given duration. PMP estimates, including generalized and statistically based, have been made in the United States in the early 60s. Generalized meaning from the graphs. There's a book on every state that tells you everything about how to calculate the PMP. And there's another gentleman, I can't remember his name right now, it's in my book, in my hydrology book, that he gathered all the data. He wanted to get a procedure that will be one equation, and he did develop the one equation. He said the PMP is usually 21 standard deviations removed from the mean. 21 standard deviations? That's a heck of a lot. Well, if you remove you get the mean, and then you get the standard deviation of the data, and then you move to the right 21 standard deviations, and you, lo and behold, get the PMP according to this gentleman that put together this study in the year, I believe in the middle 70s, because when I wrote my book in the 80s, I already picked that idea up. I think it's a good idea. Furthermore, it is not just a good idea, it's an idea that could be applied all over the world, because if somebody out there doesn't have the maps like the US has, they can't take the Arizona map and put it into Peru. It just simply doesn't work that way. Arizona is Arizona, and it's different. Okay, so they could use this equation, generalized equation. So it's very useful. I've used it in a couple instances and compared it with the map, and not with the map, compared it with the frequency-based data. What is the return period of 10,000 years? So we go from 100 to 10,000. Gilbert White had nothing to do with the 10,000. The 10,000 had been around the world even prior to Gilbert White and prior to the PMP. So in countries lacking a generalized PMP like the US, it is common practice to use the return period of 10,000 years in lieu of the PMP. Where is this 10,000 year embodied? It is in the regulations. Like in Mexico, there's regulations for flood calculations, and they go all the way up to and including 10,000. They don't go beyond. Why? Because 10,000 is 400 generations. 10,000 years ago, you imagine 10,000 years ago, the only people I think that were up were the Chinese, which take about 11,000. Chinese civilization is about 11,000 years old. Egyptians are about 6,000. The rest below 6,000. Okay, that's as much as I know. I'm not a historian, but you know all these numbers. I don't have to repeat them for you, or you can Google it. Google now knows 98% of everything, and it's good enough for us. I think it's good enough for me. I think it should be good enough for you. Okay, although some people disagree violently with me. They want 100%, and I always say, you can never get 100% of anything. Why should you get it out of Google, right? At any rate, the value of 1,000 years has been used for many decades, the maximum return period. It is a de facto equivalent of a practicable maximum value. I'm talking not possible, practicable maximum value. Can the PMP differ from the 10,000 year estimate? It is not uncommon for a statistically based PMP to be different from a statistically based P10,000. In other words, you calculate the PMP from statistics, and there's differences in there. 10–20% differences is entirely acceptable. I already told you that an error of 30%, I wouldn't raise an eyebrow if it's hydrology. If it's hydraulic, I would, because hydraulics is more detailed and more precise. In hydraulics, I would take 2 to 3% maximum. Hydrology, 20 to 30%. Sedimentation engineering, 100%. Because sedimentation varies a whole lot. 4 or 5 orders of magnitude easily. When are return periods up to 10,000 years used? For places where generalized PMPs have not been developed, okay, and where risk of failure places human life in jeopardy, return periods in excess of 100 years to include 200, 500, all the way up to 10,000 are warranted. When we did the dam in northern Peru, We use a 10,000 year frequency, which we calculated. We calculated based on, not from data, but rather from simulation, modeling. That's what they hired me to do the modeling, to do the simulation with the 10,000 year flood. Values up to 10,000 years are used for emergency spillway and freeboard hydrographs in dam design. And here I have an emergency spillway. And then the freeboard hydrograph will use all the entire freeboard in the case of a very huge flood. We still have the freeboard. The freeboard is technically our safety factor, but we could use it because we're talking here statistics which we don't really completely know. 10,000 years, right? What could happen in 10,000 years? A lot of things could happen. What return periods beyond 100 years are used in the United States? Well, we use beyond 100 years, we use fractions of the PMP. I think I already told you. Natural Resources Conservation Service has a practice in their manuals. TR60 has a complete reference. TR stands for Technical Release Number 60 of the Natural Resources Conservation Service. They have all the design parameters for structures, small, medium, and large, actually. Although Natural Resources Conservation Service does not get into large dams. The agencies that get into large dams are the Army Corps of Engineers and the Bureau of Reclamation. Okay, are return periods longer than 10,000 years used in design? The longest return period is normally 10,000 years. I personally have not used more than 10,000 years. I have not seen 10,000 years, with some notable exceptions, used in the literature. Most people agree that 10,000 years is about as much as we are willing to go. Although I must say that now with global warming, and given the fact that a lot of people now, hydrologists of note, are studying what's going to happen in the future, then we may have to reconsider the situation. We may have to go to 20,000 because of global warming. But if without global warming, 10,000 is the norm, and has been the norm for at least 100 years that I know of. Okay. However, there are exceptions. This is an exception taken from the ASCE External Review Panel Hurricane Katrina report. You would recall the Hurricane Katrina fiasco. That was in 2007. There was a 2-year report. 2 years later, the ASCE External Review Panel, the ERP report, they came up with a statement. And look at the statement. This is fascinating. It is fascinating for me. I don't know if it's for you. Relative to what people are generally willing to accept or tolerate for dams, the level of risks to the resident of New Orleans was very high. So the issue is, what is the level of risk of the levee? The levee is a small dam, but this levee in New Orleans was long, and there was a lot of water because behind the levee was the ocean, and there was a lot of water, interminable amounts of water, right? For instance, if the hurricane protection system, this typo in there, had been treated as a major dam, it would have needed to be designed so that the likelihood of failure would have been roughly once in 100,000 years to once in 1,000,000 years. Wrong, sir. That is really not the case. How is it that these guys thought, we thought they would know? Really. I can't tell you because I don't know. I wasn't there. But I'm telling you that that particular statement in the ERP report of Hurricane Katrina was wrong. They should have said 10,000 years. But somehow they got carried away to the number. I had never seen 100,000. I should take that back. Because in my book, in one of the chapters, at the end of the book, we're talking about 100,000 as something that is in the future, something that cannot be considered at this point. At any rate, that's what I wanted to say about that. Now, what is the return period of a flood resulting from a dam breach? Now, when there's a dam breach, and do dam breaches occur? And the answer is yes, they do all the time, as a matter of fact. Why do dam breaches occur so often? And the answer is because I tell you, 40 years ago, there were 50,000 dams in the United States. 50,000. That was 40 years ago when we did a study, when we looked at the literature. Now, it'll be 70,000. That is my guess. Google that. How many dams in the United States? Mid-size, not just little ponds, but mid-size dam, mid-size to large dams. It should be certainly more than 50,000. It would be like 60 or 70,000. So be it. Let's say that that was the number. Okay. Interestingly, though, most of those dams are earthen dams. Why is that? Why do we build earthen dams anyway? So that they will breach. And the answer is we have no choice, because the only time we can build a concrete structure is when there's rock below. If we have a foundation and the foundation is soil, then we cannot put a heavy structure on top of it because it'll settle, it'll cause all kinds of problems. So, long story made short, when there's rock in the foundation, you can build a concrete structure. Furthermore, in the 20s, 30s, 40s, the era of large dam concrete construction in the United States, most of the sites that could be amenable to a dam as a dam site were already taken. There were other sites that had to be built. So we've been building earthen dams for almost 50 to 70 years. We started with Terzaghi. In 1924, he wrote a book called Soil Mechanics, because this is soil mechanics. This is not hydraulics. So therefore, the dams are going to breach. The largest and more famous breaching of the dam was the failure of Teton Dam on the Snake River. And I'm not sure if it was in the Snake River. I've been called into that attention. I think it was in the Teton River. Suffice it to say that it was in Idaho, and it was on the 5th of June, 1976. Why did this dam breach? It was poor design. The designers were unlucky. They did a few things. They thought it was going to work this way, and it worked that way. They did a whole bunch of injections to control the filtration, and that didn't quite work. It was hit and miss. So it failed. They actually never put together the dam. The dam was left as it was, and it looks like this. Interestingly, though, this dam failed in about 3 to 4 hours, which led us later on to examine why is it that it takes 3 to 4 hours to breach. Because typically in a dam, like a concrete dam, it fails in 5 minutes, and the huge wave coming out in 5 minutes. But this dam didn't have a huge wave because the flood that came through the dam had to breach the dam, and while it was breaching the dam, it was attenuating the flood. So the flood was not that large. Now, considering this, then we would say now safely that if there's a breaching of an earthen dam, it would take some time. Typically, it would take between 2 to 3 hours. That's the average. If it were a concrete dam, it could breach in five minutes. But the concrete, particularly the arch dams, but there are not that many arch dams anyway around the world, so we're going to pass on that one. But let me say that I have not seen, or I have not been appraised of a failure of a concrete dam. Those concrete dams were built in the 20s, 30s, and 40s, and they're still there up. And they probably will be up for a long time to come. Okay? But the earthen dams, they fail all the time. Can return periods vary within the same project? And the answer is yes. You can have a huge project and various return periods for various projects inside. Will global warming affect the design? Yes, positively. Why? What is global warming? Global warming is an increase in the mean temperature of the world. And right now, studies have said that in the last 50 years, the increase has been 0.5 degree Celsius, or perhaps even 1 degree Celsius, depending on who you talk to. And that's not a whole lot, but in fact it is. It is a whole lot. What can I say? You know, the variation in degrees Celsius is from 0 to 30, 35, but in fact, suffice it to say at this point, it varies. The temperature varies, but 1 degree Celsius increase in the mean over the last 50 years is considered a lot. And why is that? Well, that's because of the carbon dioxide. So the temperature is increasing, and that is causing more evaporation from the oceans. And that evaporation from the oceans has to go somewhere. Now, if that evaporation from the oceans stayed within the ocean, we would have no problem. It evaporated and it rained right back in the ocean, and that's not going to cause damage to us. Unfortunately, though, there's a difference in albedo between the ocean and the land. The land has higher albedo, 0.15, while the ocean has 0.07, double the albedo. And that effect of differences in albedo has a tendency to move the water inland. So if there's more water evaporating from the ocean, more water is going to move inland. Now, had it not been for global warming, we still thank nature that she's moving the water inland, because if she generates the water in the ocean, because all water, all evaporation, that's the advective precipitation, is being generated in the ocean. So if it doesn't move inland, then we're stuck. As a matter of fact, we have a specific case in Peru, the country where I originated more than 50 years ago. The entire coast of Peru, a stretch from exact end of the north in Peru to the end of the south, about 2,300 kilometers, 1,500 miles, is a desert. But it's a strip of only 20 to 30 kilometers. But it's a zero precipitation desert, some of the driest areas in the world. And why is that? Because there's an inversion in the ocean right next to it, and it does not let water move inland. The moisture that evaporates doesn't move inland. So it doesn't move inland, it doesn't precipitate, it's not there, and therefore you have the one of the most arid deserts in the world off the coast of Peru. Now, another story, the Peruvians have learned how to live with that, but that's another story that is not hydrology, so we're going to leave it at that at this time. Who chooses the return period? The engineer, in conversation and consultation with the owner. Different return periods, all the way from 5 to 10, we already started, all the way to freeboard hydrograph for a Class C, that is a very important dam, 10,000, or the PMP, highway design, etc., etc. So that is the question and answer. In the interview, I already talked about it, so I'm going to skip that. The ASE Hurricane Katrina External Review Panel, there it is. You can read it if you're interested. What caused the problem in New Orleans in the year 2007? I do believe there was 1,000 people killed, but I don't get me on that number, because I don't know. I don't know everything. But there were a lot of people killed, and there was a lot of damage out there. What was the problem? As it says in this report, quite correct, that the Army Corps decided to do this. Yeah, I believe, okay, here it is. The Army Corps decided to do this design. And the embankment, they put in here a wall, a concrete wall. And what happened was that the soil was poor. So the wall kind of leaned on the side of the pressure. And once it leaned, it started leaning, it gained momentum, and that was the end of it, and then the ocean could move in. So had the soil been strong, it would not have happened. But the soil was not strong, because that's almost muck. The soil in lower Louisiana, in lower Mississippi, in Louisiana, it's very poor quality. And this is all documented in this report. This report documents the issues of geotech issues that allow the problem to fail, rather the levees to fail. So in retrospect, the levees should not have been built like that. They should have been built normally, like you would a levee, earthen levee, but still a normal levee, not something that could tip. And if it had failed, it would have failed locally, and it would not have caused a lot of problems. It would have taken a long time for it to breach anyway. I already told you that. And it would have been pretty much mostly under control. But that was not the case. This thing happened overnight, and it went a disaster from the evening to the morning. It was a complete disaster. Since that time, the Corps has learned, and I'm sure they're no longer doing this kind of design. They're actually replacing everything that is considered to be something that could fail in the same way. Why did the Corps do that? Well, they were looking for savings. You know, there's always, in the issue of building projects, there's always savings. And you can save only so much, because if it fails, then it's come back and it's going to hit you on your face, on the face. Okay, so we have here okay, and then the quote that I already quoted you, but let's repeat because it's an interesting quote. And I'm going to give you my thought of it. It's just my thought of it. Relative to what people are generally willing to accept, the level of risk for the residents of New Orleans was high. If the hurricane protection system had been treated as a major dam, it would have needed to be designed so the likelihood of failure would have been roughly 1 in 100,000 or 1 in 1 million. That's too much. That's wrong. How did this erroneous concept slip? How did it slip into this important report? And I'm going to guess, and allow me to do a guess, I can guess anything I want, that the head of the project was a geotech, and maybe he reviewed the report and so forth, and you know, the specialties. There's people specialists in water, hydrology. Even in water, you have water resources, hydrology, fluid mechanics, and so forth. There's, even within a specialty, you have subspecialties. And in this case, I think he slipped, he didn't quite know, and other people did not correct him. If I had been there, I would have said, just take a 0 out of the first one and forget about the second one. That would have been correct for all practical purposes. If you have any questions whatsoever about the subject matter, just give me a buzz, meaning send me an email, and I'll try to respond as quickly as possible. You guys know that I do respond within a couple hours. Thank you. Bye-bye.